Okay, low versus high resolution proton nuclear magnetic resonance. So we looked at HNMR spectra already, but so far all we've really cared about are the low resolution spectra. And in a low resolution HNMR spectra, each chemical environment for hydrogen just appears as a single signal. So just like one peak could be represented as a single line or just one sort of triangle looking peak. But if you look at some of those spectra under higher resolution, you can see that those individual signals can actually be divided up into multiple peaks. And the ways that they can split are known as splitting patterns. The multiple peaks are due to the influence of the magnetic fields of the neighboring hydrogen nuclei, the neighboring hydrogen atoms. So the hydrogens that are on the neighboring carbon atoms to the hydrogens that you care about. I know that all sounds a little bit confusing when we explain it that way, so we're going to look at some examples that hopefully will clear that up. Since we talked about how each hydrogen nucleus can have two different spins, for any neighboring hydrogen nuclei, there's actually two very different, slightly different magnetic fields that it can create. And so that causes very slight differences in the splitting signals that we pick up in the HNMR. So this is an example of a high resolution HNMR, and it's looking at ethanol. And so what I mean by the splitting patterns is that, well, in one case you have just one single peak here, this red H, but for this one you actually end up with not one but four peaks. And for this hydrogen environment, instead of just one peak, we're getting three peaks. So now we're going to talk a little bit closer on why those peaks are what they are, why they get that splitting pattern. Okay, so if you're a hydrogen atom and on the next door carbon atom, there are zero other hydrogens. So you're a hydrogen that's on a carbon, but on the neighboring carbon, there's actually no other hydrogens. Well, there's only, therefore, one environment for you. You're not affected by any neighboring carbon atoms. And so therefore, whether it's a low res or a high res HNMR, it's going to show up as one single peak. So you're just going to see either a simple line at that spot, or maybe one big peak, kind of like that. That's a little squiggly, but you get the idea. Now, if you are a hydrogen on a carbon, and that's next to a carbon that has one hydrogen. Okay, so to try to clarify. So let's say we're looking at a peak for this hydrogen, or for a group of equivalent hydrogens. And on the neighboring carbon atom, there is just one hydrogen. Okay. So there's some other stuff, maybe some other carbon chain here. And it could actually be that we're talking about a chemical environment that has three hydrogens in it. So we're looking at the peak for these hydrogens here, these three hydrogens, and those three hydrogens are next to one other hydrogen atom. Okay. So here's the thing, this hydrogen that I just circled in red can either have an up spin on its nucleus, or it can have a down spin on its nucleus. And those different spins have a slightly different magnetic field, and they influence the magnetic signal being given off, the radio wave signal being given off by this hydrogen environment. So rather than just getting a big peak that represents the three different hydrogens that exist on this CH3 group, what you actually get is two slightly different peaks. So when you see this readout, you're going to get something like this for this chemical environment here. Okay, so because it's next to one hydrogen and that hydrogen nucleus can spin in two different states, it creates two slightly different possible magnetic states for this chemical environment. Okay, and so that's what we would call a doublet. All right, now same example, same idea, but now let's take this, let's copy it, and let's move it down here. Ooh. Now, instead of being next to one neighboring carbon atom, we're going to be next to two neighboring carbon atoms. Okay, and so again, the ones I care about, the neighboring carbon atoms I'm talking about, are these two right here. Okay, so it continues to get more complicated. If you've got two, now they could both be pointed up. They could both have up spins. They could both have down spins. And then they could have one or the other. So you could have one up and one down. But actually, there's two different ways that you could have one up, one down. You could have this carbon be up and that carbon be down, or this carbon be up and that carbon be down. So the only reason I point that out is that this middle sort of magnetic field that gets created is twice as likely as these outer ones, where they're both up or they're both down. So we can see that there's actually three slightly different magnetic fields that can be created by these two neighboring carbon atoms. And we see that the middle one is twice as likely. So the pattern that we end up getting in a triplet is you get a little peak, then you get a tall peak, and then you get a third peak. And it looks something like that. Now this middle peak is probably too high. It should be about twice as much area as the side peaks. But you do see three little peaks, and the middle one is longer than the side peaks. Okay, and then the most that you would be asked, I don't think I need to draw it again, but it would be if your carbon environment is next to an environment that has three neighboring hydrogen atoms. This is the highest that you'd really be asked to think about on the IB exam. You may see the pattern that we're getting to here. When there's zero neighboring hydrogen nuclei, you get a single peak. If there's one neighboring hydrogen nuclei, you get two peaks. When there's two neighboring hydrogen nuclei, you get three peaks. And so if we keep with the same pattern, when there's three neighboring hydrogen nuclei, you get four peaks. And what are they going to look like? Well, there's one way that they can all be up, and there's one way that they can all be down. But then you can have two up and one down, or you can have one up and two down. And those are slightly different from one another. And there's actually three different ways, because there's three hydrogen nuclei, that you could have two up and one down. And there's three different ways that you can have one up and two down. And so what that means is that the middle ones are three times as likely to happen as the side ones. And so you end up with a peak, a little peak, and you get a tall one, you get a tall one, and then you get a little one. And so this is what a quartet looks like. So these are the various splitting patterns that you are likely to see. There are more complex ones when there's more than three neighboring carbon atoms, but you wouldn't be expected to be able to analyze them for the IB exam. The really simple takeaway thing to remember is that the number of peaks, equals the number of neighboring H atoms plus one. So if you're next to zero hydrogens, then you see one peak. If you're next to two hydrogens, you see three peaks, and so on. The other thing to remember is the exception. There is an exception, like there always is, to the splitting rule, and that's that for whatever reason, the H on a hydroxyl group, so the H on the alcohol functional group, always shows up as a single peak. And trying to explain that is a little bit beyond me and beyond this course. It's just something to remember that when you see this OH group, even if it's next to a carbon that has two or three hydrogens on it, it always shows up as a single peak. Okay? And splitting patterns are just sort of one more piece of useful information that we can use to help confirm things about molecular structure. So if we look back at that ethanol one to see if it matches what we just pointed out, here is one chemical environment. It's got three hydrogens in it. We've got this chemical environment with two hydrogens in it, and we've got this one with one. So we've got three different environments. We would expect the area, the integration trace, to show 3 to 2 to 1 ratio. But now let's think about the splitting. These three hydrogens are next to two. So because they are next to 2, we'd expect 2 plus 1 peaks. And if we look at the peaks for the 3 hydrogens here, we see just that. We see 3 peaks, right? So this is a triplet pattern, and it's due to being next to those 2. If we think about this hydrogen environment, these 2 hydrogens are next to these 3. And so we expect to see 3 plus 1 peaks. And if we look where they are, we do indeed see the 2 little peaks on the side and the 2 bigger peaks down the middle. So we see a quartet splitting pattern. And then if we go to the hydroxyl group, we said hydroxyl is that exception. And so we just see the single peak. Even though it's next to these 2, and we would probably predict that we'd see a triplet peak there, the OH is the strange exception, so we only see the 1 peak. So just, now that we've seen HNMR low and high resolution, just to recap it, your steps are that first, look for the number of different chemical shifts, because that will give you the number of different chemical environments for your hydrogen atoms. Second, look at the height of the signal or the integration, the area of the different signals, and that will help you determine the ratio of hydrogens at each environment. You can also look at the chemical shift values and compare them to the ones in the data booklet to help you determine what the different environments are. Are they on methyl groups? Are they in the middle of a carbon chain? Are they the H on a hydroxyl group? Are they the H on a carboxyl group? Are they next to an alcohol group? Things like that. And now finally, we can use the splitting pattern to further confirm how many hydrogen atoms the exact hydrogens we're caring about, our chemical environment, are next to. So it helps us figure out more about the structure and confirm about the neighboring carbon atoms to the hydrogens that we're looking at. So there's a lot of different steps that go into HNMR, but it's a very, very useful technique for helping us figure out things about structure.